Hello, my name is Lauren Thompson. I'm a mechanical engineering student at Georgia Tech. I am currently enrolled in Mechanical Engineering 3210 with Dr. Rashidi, Design, Materials, and Manufacture in the semester fall of 2024. Please note that everything in this video is for educational purposes only. This is me presenting my 5 selected topics for Project 3. The first topic I have selected is automation of manufacturing processes. A simple definition for automation is self-acting, which are machines that are specialized equipment and devices that follow a predetermined sequence of operations needing little human intervention. Automation in manufacturing has been around as early as the 1500s when water power began being used for metalworking, specifically rolling mills and for coinage strips. It is interesting to see how far we have come since the first use of the word robot was used around the 1920s. The 1980s was the first time we started using smart sensors, unattended manufacturing cells, and we have come an even longer way since then. Some areas of focus for manufacturing include production process, so things like machining, forging, extrusion, etc., material handling and movement, where materials and parts in various stages get moved through a plant by computer-controlled equipment with no need for human guidance, inspection, where parts are inspected automatically for accuracy, surface finish, qualities, and specifics, assembly, where individually manufactured components are assembled automatically into a complete product, and packaging, where products are packaged. The reason I like this topic and I feel it is important because it shows how historical automation influences automation today. It is interesting to consider engineering from a historical perspective because that's not one we get very often as engineering students. It is also really important to understand current automated processes and improvements for them, basically looking at how improvements from the past can affect improvements for today. This also makes us more well-rounded and overall educated students. Additionally, it is a fresh topic to break up the constant focus on technological advancements to take a look back at history. Some capabilities and applications of automated manufacturing include that many aspects of manufacturing achieved over time is integrated to improve the overall modern product quality and minimize human risk and thereby reduce labor costs. Improvements in control of production and organization leads to reducing manufacturing costs. Additionally, improving the quality of products by using repeatable processes become even more reliable on time. This reduces the possibility of human error and human risk, reduces damage to the workpiece, reduces inconsistencies, and constantly new evolving technology that can be easily integrated. The photos here show historical timelines of the evolution of manufacturing, just as an example of how far automation has come. Some limitations include that initial investment in machines, software, and materials can be a significant upfront cost. Additionally, machines oftentimes need regular maintenance, which can be timely and costly. Also, machines can break down, which lead to costly downtimes. Since automated systems are often designed for specific tasks, modifications to these systems can be limited and costly. Job opportunities could also be really reduced because automation reduces the need for manual labor. And lastly, because automated processes do not have visual inspections, there is the potential to overlook quality issues and imperfections. Notice the images on this slide showing examples of the limitations of manufacturing when machines break. The second topic I have selected are composite materials and their applications. Composite materials are engineered materials made by combining 2 or more distinct materials with different physical or chemical properties. Some combination of these consists of polymer matrix, metal matrix, and ceramic matrix composites. Composites date back to 4000 BC, where some of the oldest examples include straw added to clay to make bricks stronger. There's a variety of different kinds of plastics or reinforced plastics. Some include carbon fiber reinforced plastics, which combine the low density, high strength, and high stiffness, conductive graphite fibers, which enhance electrical and thermal conductivity, ceramic fibers that are good for high temperature applications, and polymer fibers that may be made of acrylics. I like this topic and think it is important because it is interesting that the best properties of various materials can be combined to make one really strong, really great material. It's used in a variety of different fields, including renewable energy, aerospace, the automotive industry, and those are just to name a few. A lot of problem solving and experimentation to determine what works best interests me. Additionally, there's a positive impact on sustainable engineering from composites. Lastly, composites is an interdisciplinary study because it combines chemistry, material science, and many other topics with engineering. The two figures on the left show the composition of composite materials. Composites have improved strength-to-weight ratio because they are lightweight but strong, so they're great for the aerospace and automotive industries. Additionally, they resist corrosion and extend the life of products, especially those in extreme environments where there might be extreme temperatures, a lot of chemical exposure, or marine environments. Composites are oftentimes engineered with specific mechanical, thermal, or electric properties in mind. They can withstand wear, impact, and fatigue better than a lot of existing materials, and they can provide excellent insulation for electrical and thermal uses. They can also be complex shapes and innovative designs that are difficult to achieve using other materials like metals. And lastly, composites often require less maintenance. This slide details just how diverse and just how important the use of composite materials is in the aerospace and automotive industries due to their high strength but lightweight nature. It is important to note that limitations for composites include costly materials and damage that can be hard to fix and might often result in the full replacement of components. They can be sensitive to some environmental factors, including UV light, moisture, and temperature fluctuations. Composite materials are also challenging to recycle and may not be biodegradable, so they're not very sustainable. Designing with composites often means carefully considering load paths and orientations, and that increases the design time and complexity. Last time, composite manufacturing processes can release compounds that can be a risk to human health. The third topic I have selected are additive processes. Additive processes are additive rapid prototyping operations that build layers and parts. This includes fused deposition modeling, which is outlined in this schematic, stereolithography, which is a curing of a liquid photopolymer into a specific shape, which can be seen in this schematic. Selective laser sintering, which can be seen in this schematic, the process based on sintering of less common metallic powders. And lastly, 3D printing, which I'll get more into later, but here's a quick diagram. I like additive processes because the rapid prototyping experience is very valuable for students to learn and understand. Additionally, it's fun to be able to see a full design start from fabrication and then come to the end in real life. There's also versatility to the strength and resistance of parts when you're using additive manufacturing, and it's valuable hands-on experience for students. It's often an experience that we can get as students because they don't require really heavy machinery. It's also an efficient process. Capabilities include creating complex geometry with intricate shapes and internal structures, which would be hard to do with traditional methods, reducing waste because we only have to use a necessary material and there's no need for molds or outside materials, rapid prototyping, as I've already mentioned, on-demand production, meaning there's no need for large stock components, material variety, as already mentioned, and reduced tooling requirements. When it comes to additive processes, and specifically 3D printing, as you can see shown by the photos on the left, that there's a lot of limitations because there are high initial costs. The machines and materials can be expensive at first. There's slow production speed because it's slower than the traditional manufacturing for high volume production since they tend to have automated systems and assembly lines, whereas additive processes don't. There's limited material properties. There's also post-processing that has to happen. There are size constraints due to the build volume of printers, variable quality and consistency between prints, design limitations, and lastly, broken machines can cause downtime because they take time to repair. Another topic that interests me is turning, and specifically on lathes. The definition of turning is a simple machining process where the part is rotated while being machined. This can produce straight, conical, curved, or grooved workpieces that include shafts, spindles, pins, and even more. There are a variety of different operations while turning. I like turning because the technique merges engineering with skilled artsman and craftsmanship. It's applicable to a variety of different materials. It's easy but a beneficial machining skill for engineering students to learn. Lastly, it's quick, precise, and a versatile machining process. Capabilities include high precision machining with a variety of different materials, excellent surface finishes, quickly and efficiently shaping material. In addition, CNC lathes enable automated computer-controlled lathing that is very precise and good for large-scale and complex manufacturing. Some limitations with turning include that they are designed for creating rotationally symmetric parts, so producing anything asymmetrically or complex is really difficult. The size of the workpiece is additionally limited by lathe diameter and capacity and bed length. Very hard or brittle materials can be challenging to machine and can cause excessive tool wear. Extremely high-quality surface finishes can be difficult. Cutting tools can be worn down quickly while turning. Thin or long workpieces can also vibrate while turning. Lathes require skilled operators to control speeds, feedbacks, and tool positioning, which can lead to long trainings. Though CNC lathes reduce this, conventional lathe work can still be pretty labor-intensive and not as efficient. The last topic I have chosen is computer-aided design and engineering. A summary includes using computers to create drawings and designs of product models that are associated with interactive computer graphics. There are many commercially available CAD programs, including SolidWorks, Pro Engineering, Vectorworks. These softwares can help identify potential problems like excessive loads. Additionally, CAD databases have a lot of materials and specifications and manufacturing instructions that can be easily accessed. There is a 4-step design process using CAD outlined here. I think this is an important topic because students can experience the benefits of CAD modeling nearly every day. It's used in industry by professionals for rapid prototyping. It allows us to explore creativity when it comes to design engineering. It's very efficient, and very new innovative technologies and updates are easily accessible. With CAD, engineers can have highly accurate designs, precise measurements, reduce human error. CAD is also used across industries, including engineering disciplines, architecture, automotive industries, and even more. It automates repetitive tasks and allows for real-time collaboration as well. Some drawbacks with computer-aided design include that CAD software and necessary hardware upgrades can be expensive. Different CAD software may have compatibility problems, and that can cause delays in file sharing and collaboration. Virtual models may not capture real-world applicable variables, so physical testing is always so necessary. Lastly, CAD files can be vulnerable to unauthorized access or intellectual property theft when sharing digitally. These are the sources I used for this project. Thank you so much for watching, and of course, please remember that this was for educational purposes only. Thank you.